couple of years ago, shortly after I finished my PhD, I just moved to Boston to start a postdoc. I got a phone call from someone in California asking me if I would fly there to speak with a billionaire named Yuri Milner. And he wouldn't give me many details. He just said that it had something to do with interstellar travel. So I naturally thought this was pretty intriguing. I said yes, of course. And I immediately got thinking about what this could be about, right? As an engineer, one of the first things that came to mind was the rocket equation. So here's a little rocket science 101 for everyone. The rocket equation basically tells you if you want your rocket to reach a certain speed, how much fuel you'll need, measured in kilograms, say. So one of the key takeaways from this is, let's say your rocket has reached a certain final velocity when it runs out of gas, and you want it to go just a little bit faster. That means you'd need just a little bit more fuel right at that point at the end of the trajectory. But that would mean that your rocket weighs a little more now at the end of the trajectory, and therefore would need, at the instant in time just before that, a little bit more fuel again to lift the extra weight. And now it weighs more at that instant, and again at the instant before that would need correspondingly more fuel to lift that extra weight as well, right? So you can see there's a sort of compounding effect here, and if you go all the way back to when you launched, you need a lot more fuel just to go a little bit faster. So this is sort of a compound interest kind of thing, right, if you like. If you're a little bit more mathematically inclined, you'll recognize this as exponential growth, right? So what the rocket equation tells us is that the mass you need in your rocket and in fuel goes exponentially with the velocity you want to reach. And to put this in some concrete terms, if you think about a modern rocket like a SpaceX rocket, if you wanted to double the speed that rocket could reach, you'd have to increase the fuel mass that you start out with by a factor of 30. So this is clearly not really a winning game. We can't really win at this game, pushing up this very, very steep exponential curve, right? So we kind of need to think out of the box a little bit and figure out some other way. So now to give you a little bit of insight into the scales we're talking about, here's kind of our stellar neighborhood, our closest neighbors, right? At this scale, we would be way inside that sun disk on this chart. And our nearest neighboring solar system is called Alpha Centauri. It's actually 3 stars that all co-orbit each other. There's 2 larger stars that are about the size of the sun called Alpha Centauri A and B, and there's 1 smaller red dwarf star called Proxima Centauri. So those are at about 4.2 light years away. As you keep going, you get to Barnard's star at about 6 light years, and past that, there's actually several more options that we might like to go visit within about 10 light years. To put this in some context, the fastest and farthest spacecraft ever launched by humans has just barely left our solar system. It's called Voyager 1, and it's about here on the plot, about halfway to that Oort cloud. So we need to think a little differently, right? And so what I did, go out to San Francisco and speak with Mr. Milner, and when I learned what they had in mind, it was very interesting, but it was actually a very old idea, which was kind of interesting to me. And basically, it comes down to wind. So photons of light carry momentum just like the wind here on Earth, right? And just like a sailboat, we can build sails that capture this solar pressure, right? And this is a real technology. This exists today. This is a real solar sail called NanoSail D that flew a couple of years ago. And there's another solar sail mission launching this year called LightSail 2. So this is real. We've built these things, and they exist. The problem is using just light from the sun, a solar sail like this one will only gain about 1 meter per second in velocity per day. So at that rate, it would take it about 30 years to reach the same speed as just a chemical rocket. And again, tens of thousands of years to reach, say, Alpha Centauri. So the key idea behind Breakthrough Starshot is actually to essentially build a better sun. So what that looks like is this roughly kilometer scale, roughly 100 gigawatt laser array. So we built this giant laser. We built a lightweight light sail spacecraft that's a couple of meters across. The sail is a couple of meters across, and the spacecraft itself in the middle of that sail weighs maybe 10 grams. So we build this tiny spacecraft. We shoot it with this massive laser. It accelerates at about 60,000 Gs. This is similar to a shell coming out of a cannon. And after a couple of minutes, it reaches about 20% of the speed of light. At 20% the speed of light, now it's coasting. It takes about 20 years to travel the 4 light years to Alpha Centauri. Once it gets there, it has about 1 or 2 hours flying through the Alpha Centauri system, during which it can take pictures, make scientific measurements, and then send this data back to us, right? Keep in mind, 4 light years away, it takes actually 4 years for the data to get back to Earth. So altogether, this would be something like a 25-year-long mission, which is within a human lifetime, is within kind of actually the time scale of missions we fly today on spacecraft, right? Voyager's been flying for 40 years. So this is all incredibly hard. But I think the key takeaway here is this is not science fiction. This is not Star Trek warp drives. This is all difficult engineering. We understand the physics. In principle, we understand the technologies involved in doing this. It's just engineering. And actually, there's very encouraging clues that sort of some of the technologies you need to do this are maybe just over the horizon, or maybe pieces of it already exist today. A few examples of that. First, we need a really big laser array, not just a single laser, right? Many lasers, many powerful lasers. And this is an example of one of these high-power lasers, actually. This one was built for the US Army for maybe less benevolent purposes. But it's 19 high-power lasers that are combined together in what's called a phased array to form a single, more powerful beam. So we can do this today. It's a matter of scaling up. And there again, there's some hope. It turns out that the cost of lasers, if you measure it in sort of dollars per watt, is following a Moore's law-like trajectory where the cost per watt is actually halving about every couple of years. So maybe in a decade or two, not only will we have the technology to do this, but also the economics will work out, right? Once we build this laser, there's another hard problem, and that's getting the laser beam through the atmosphere in one sort of focused collimated beam, right? The atmosphere distorts light because of turbulence. This is why stars twinkle. But in the last decade or so, there's been amazing progress made in adaptive optics for large observatories. This is a process by which, by sort of tweaking the mirrors, they can actually correct for these atmospheric disturbances and refocus the light. And this is exactly the sort of thing we might be able to do in the other direction to keep our beam focused as it travels through the atmosphere. When the beam gets to the sail, the sort of business end here, we also need a sail that can take all of that power without just cooking. And here again, there's been amazing progress in the last 10 years or so with what are called metamaterial mirrors. So this is an example of one built at Harvard a couple of years ago. And what's going on here is by micro-machining these materials at very small scales, at scales about the same as the wavelength of the light, you can make essentially a perfect mirror that has 100% reflectivity and doesn't absorb at all. This mirror here, in fact, can take power levels much higher than we actually need for Star Trek. So here, Starshot. Excuse me, not Star Trek. So this is a technology, again, that actually exists today, and it's a matter of scale, right? And finally, we need this 10-gram satellite, right, that's going to ride this sail. Here is actually how I got involved in this project. This is my PhD work. This is the world's smallest satellite. It weighs 4 grams, in fact, and there's a couple of these on orbit right now. If you're a ham radio operator, you can go out in your backyard with an antenna and listen to these, in fact. So here we have all of the subsystems that you need to make a spacecraft function in orbit and talk to it. And I think, again, there's hope that in 10 or 20 years, with the advancements in electronics, we'll be able to take something on this size scale and have all the functionality we need for this interstellar mission. So finally, why is this worth doing? Why should we invest the money required to do something like this as a society? Well, here's a picture of the Alpha Centauri system. The 2 bright stars are Alpha Centauri A and B, the larger stars. And in that little red circle is Proxima Centauri, the little red dwarf star. About 1.5 years ago, an exoplanet, Proxima b, was discovered in the habitable zone around Proxima Centauri. So this means that it's in the right range from the host star to potentially support liquid water and potentially support life. So the closest neighboring solar system to us has a potentially habitable planet around it. I think most of us would agree this would be a pretty interesting place to go take some pictures. So I think at the end of the day, this whole thing is really about some of these most fundamental, deepest of questions, right? It's about what's out there and are we alone in this universe? And I'm hopeful that in 20, 30, maybe 50 years, we'll get another picture like this one. This is the famous pale blue dot image taken by Voyager 1 as it left our solar system, looking back towards Earth. And Earth is this little blue speck there towards the right of the picture. So I'm hopeful that in a couple of decades, we'll get a picture like this, not looking back at Earth, but looking towards a new Earth. Thank you.